Ladies and gentlemen, dear colleagues, welcome. I'm Zdenek Hanzalek, and you are watching the 37th talk of the scheduling seminar. Today, I'm happy to introduce Vincent. He made his PhD in 1999 on multi-objective scheduling with Jean-Charles Biot. And he is working in Laboratoire d'informatique fondamentale et appliquée de Tours at École Polytechnique de l'Université de Tours in France. His favorite research topics are moderate exponential time algorithms for scheduling, bi-level scheduling, machine learning and operational research, and optimization and operations research in general. So, Vincent, it's great to have you here. Please, the floor is yours.
Thank you very much, Zdenek. Thank you for the kind invitation. So today it's my pleasure to present you this piece of research, let's say, on Matheuristics and application to scheduling. So this talk will be more talk oriented towards computation and how to solve in practice scheduling problems. Well, let's start. Okay, so we first start by saying what is a Matheuristic. And well, in the past, when I was used to speak with people about Matheuristics, and when I said, oh, you know what, I'm doing Matheuristics, people then heard meta-heuristic. There was a kind of mental bias, and they heard meta-heuristic. So, well, Matheuristics are not meta-heuristics in the sense genetic algorithms or whatever. They are very particular kinds of meta-heuristics. So that's why I wrote Matheuristics are not meta-heuristics, but kind of sort of meta-heuristics. And they are particular meta-heuristics which are based on the use of an IP solver. So when you solve your problem heuristically, at the point of the heuristic, you say, let's solve some IP formulations, either of my problems, either of subproblems. That's the main line of Matheuristics. If we look to a definition of such algorithms in the literature, we can just find out a broad definition, very large one. Matheuristics is kind of hybridization between mathematical programming and classic meta-heuristics. So it's not something really fixed. There is not a unique framework for such algorithms, which means that basically, if you have a scheduling problem, if you have an IP formulation and you just run your solver within a given time limit, well, then you get to Matheuristics. That's a very basic one, but you get to Matheuristic. So for sure, we'll see something different in the remainder, but that's the starting point. One may ask, what is the interest of Matheuristics? What is the interest of using an IP solver, which is basically working in an exponential time, to solve heuristically a problem? Well, the interest is that somehow, if you have a Matheuristic, you'll use a black box solver, which efficiency will evolve a long time. So more time is spent on the solver and more efficient will be your heuristic in the end. So that's the big advantage. So if you can somehow design a heuristic which leverage of the IP solver, but reasonably in terms of time, then you may get something that is really efficient, and that will become more and more efficient in the future without changing any line of code. Well, the first thing we can do is have a look at the literature. Is this kind of algorithm often used in the literature so far? To answer this question, I just Googled some keywords on Google Scholar. I just first, to have a reference, I Googled the keywords taboo and scheduling. And then, as you can see on the chart, there are tons of answers, like almost 45,000 papers were just the reply of my query. And then I Googled just the keyword Matheuristics. And then you can see that there is really few papers by comparison to just taboo and scheduling. And among these papers on Matheuristic, most of them are dealing with Matheuristic and scheduling. So from this chart, what we can derive is that finally, dealing with Matheuristic is quite recent. The increase of papers significantly date back from 2010, 2015, maybe not earlier than that. And the other point is that very few papers can be found in the literature. So it's still a kind of heuristic algorithm or framework that has not been really considered for scheduling problems. And if you look at the papers, in fact, they have the papers which have been published, they mainly deal with routing problems in which there is a scheduling component. That's why these papers were also in the results of my query when I Googled that. And if you continue looking at all these papers, or at least at some of these papers, you see that finally there are many different Matheuristics in the literature, and that it is really hard to just identify one general definition or framework for a Matheuristic. There are really a lot of different ways to combine IP solvers and meta-heuristics. But somehow we can classify all these papers into three different boxes. They are the papers which deal about constructive Matheuristics. In these approaches, the IP is used to iteratively build a solution to the problem. It's like if you have a greedy algorithm and the priority is just the solution of an IP solver. That's the main idea. You also have papers which deal with using the IP in the context of a local search. And these are called local search Matheuristics. And these are, in my opinion, very interesting. It's just use the IP to explore the neighborhood of a current solution. And you also find some papers which are, well, which consider the embedding the IP into an evolutionary algorithm. Well, I'll not talk about this category of algorithms further on. I will mainly and only talk about local search Matheuristics. And my goal is not to tell you everything about these kind of algorithms. It's just to give you a feedback on my personal experience when using Matheuristics like local search Matheuristics. That's it. Well, let's start. So we consider only local search Matheuristics, and then it means that we can see these algorithms like as large neighborhood search heuristics, you know. So you have the search space, you start with an initial solution, S0, and after some iteration, you have a current solution, which is, let's say, denoted by ST at iteration T, and then you need to define the neighborhood of the solution ST, and this neighborhood is denoted by N of ST. And the idea is to have a large neighborhood that you explore just by solving a mixed integer formulation. And in this neighborhood, you want to compute the best solution in the neighborhood that you call ST plus 1. This can be seen as an intensification phase. You intensify the search around ST in its neighborhood, and you don't use any classic operator, neighborhood operator, you just solve a MIF formulation. And in case, for sure, when you don't have any improving solution in the neighborhood, then what you may do is just do some diversification also by solving a MIP, and then you just get out of the neighborhood, jump in somewhere into the search space, and to get the new next solution ST plus 1. That's the main very general line for a Matheuristics. Let us go back and present more details about intensification. So you start with an initial solution, and you start with a MIF formulation of the problem. And for sure, the choice of the formulation is very, very important. If you start with a very weak formulation, that is a formulation which is really bad to compute an optimal solution, then there's little chance that this IP formulation is of any use in the Matheuristic. So you need at least to start with a pretty good model. And you have your initial iteration and your initial solution. At a given iteration, you have solution ST. Okay. To ST, we associate the variables xt, which are typically for scheduling problems, which are binary variables. And from these variables, you have to define the notion of neighborhood. And finally, what you would like to do is to optimize around ST, so allowing few variables xigt to be changed. And you'll measure the number of changes in terms of these binary variables. The first way to do that is to use what is called variable fixing approaches. Like first you determine a subset ST of variables, and you say, in my model, I add the constraints that these variables will not change of values with respect to my current solution ST. So you say to the solver, compute a solution in which the value of xig is equal to the value of xig in solution T for any variable xig from set ST. So you fix some variables and you leave the solver, you let the solver solving the subproblem that you have. That's the first approach, the first thing that you can do to define the notion of neighborhood. The second, in this category of methods, you have various methods that you can find in the literature, like VPLS or INS, fix and optimize, and so on. There is another way to define neighborhoods is to use a distance, like what is done in local branching for those who know about local branching. Typically, again, you determine a subset of variables, ST, but you say now that you'll count the number of changes from the solution that you'll compute to the solution ST that you have. So you say, for instance, you can use the Hamming distance, which is denoted here by delta of ST, and use delta of ST is the number of variables that will change from ST. And you say this number of variables that change is no more than k, and k is a given parameter. So it's a bit more flexible than variable fixing, because you don't say I fix these variables, you just say to the solver, find a solution which is distant of at most k changes from the current one. That's the two main, let's say, ways of doing of defining a neighborhood. First, we'll see an application of notably VPLS on a scheduling problem. So VPLS uses a neighborhood based on the variable fixing. And I'll deal here with the solution of two-machine flowchart problem, where I have n jobs, and each job G is defined by processing time PGI. And well, everybody knows about this problem. So all jobs must go first on machine 1, next on machine 2. We denote by CGI the completion time of job I on of job G on machine I. And what we want to do is to minimize the sum of the completion times. And the schedule here can be just denoted as a permutation sigma of the jobs. So for this problem, what we can do is use a direct position-based IP formulation, something very straightforward. I've set variables xig as Boolean variables, and I say xig equal 1 if job G is in position I and the 0 otherwise. These are my basic variables, and clearly from this definition of variables, we can sketch the IP formulation. The initialization of the Matheuristic is given by a recovering beam search algorithm, which has been also proposed by De la Croce, Girardi, and Tadei in 2004. And from this solution, which is also still a good solution, we'll see that the Matheuristic improve it. So that's the starting point. Now, neighborhood definition. So I have a schedule, ST, as in on my example here, and I will define a window of positions, which is my gray area in the schedule ST. For instance, I can say that it's a window of length H, and that starts at position R. And in the original paper, it was considered that H was equal to 12 and that R was picked at random. So you have a window of positions. And from that, what you can say is that the neighborhood of ST, to define the neighborhood of ST, you fixed the set ST of variable xij, which corresponding to job and positions which are outside the window. So in a sense, you say, I fix 115 at the beginning of the schedule and 6 to 14 at the end of the schedule. And what I will do is that I will reoptimize in the window, okay? So I will just call the IP formulation on the problem that has only 12 jobs and all the other jobs are fixed. So this kind of approach with a window of positions, and window can for sure change along the sequence. This approach is well suited for permutation problems, for sure. If your scheduling problem is just permutation problems, I would say use that approach. It's quite natural. And in the Matheuristic, what did the author do was to select randomly a value of R, so of the starting position of the window, which on my figure correspond to the fact that you have your current solution ST, and you generate randomly, you select randomly a neighborhood around ST, and you optimize in this neighborhood. You solve the IP, and if you find an solution improving ST, then you stop there. So your strategy is first improving neighborhood, and then you continue, you iterate, you go to the next iteration. And in their algorithm, the author says, okay, we stop after a given time limit is reached or you can't find an improving neighborhood. So there is no diversification in this approach. So we have the main line of the Matheuristic. Now we just, okay, we solve the problem. So we randomly generate instances and we see how it works. So in their paper, the authors said, okay, H equal 12 is a good trade-off between time spent at each intensification phase and trade-off with the quality of the computed solution. So H is not too small so that the Matheuristic will be efficient, and it's not too large so that it's not too time consuming. And this can be for sure understood, the way to pick up this value. It results from preliminary experiments. I just put here a very simple table that corresponds to results obtained for instances with 100 jobs and with the time limits of 60 seconds. So the Matheuristic stops after 60 seconds. And what I did in these small experiments is that I ran the VPLS, the Matheuristic, also ran a lower bound. And to validate the framework of the Matheuristic, what I did is that I also ran Cplex, the solver, with the same time limit than the Matheuristic. And if you look at the results, you see that VPLS, that the first cell, is at 0.26% of the lower bound, while Cplex truncated in time is at 0.46%. So VPLS improves upon Cplex truncated in time, meaning that this validates the interest of the mechanism of the window of positions and the local reoptimization. And you have similar results for higher size problems. And in fact, for instances with less than 300 jobs, that's the best state-of-the-art heuristic for this problem so far. And it's competitive for higher size problems with another heuristic called SOJ, or something like that, because the Matheuristic is really time consuming. So for large instances, faster heuristic may become more competitive. Now we have to ask ourselves, what is the impact of the random choice of R on the solution that is computed by the Matheuristic? So to do that, what I did is that I just I did around 50 times the Matheuristic on the same instance with 100 jobs, and I just stopped after 60 seconds. And in this chart, what you can see is the distribution of the values of the solutions that I obtained. So clearly, there's a solution that appears next time, 9 times, sorry, which is the solution with the value 200,729, 729. But you can see also that there is a large spreading of the values. So you don't always have the same solution. So my first question was, oh, is it due to the limit of time which was too small? But the answer to this question is no. In fact, on the average, all these 50 execution of the VPLS stopped after, on the average, 36 seconds. And at the worst case, the longest execution time was 52, so below the limit, meaning that the Matheuristic stopped because it got stuck in a local optima. That's the point. So to improve this approach, to improve this mechanism, we will have either to have a better strategy in selecting the neighborhoods than just doing random, or introduce diversification when we get stuck into local optima. That's the first point. So if we do a first conclusion on this kind of approach, we can see that they can be really efficient, and they are really real efficient extensions of standard local search heuristics. And these experiments show that there are some points of attention. First, okay, it can be stuck into local optima, and this is due to the random choice of R. And so what are the alternatives? Up to now, the alternatives may be just like, okay, I try all the possible value R for a given solution ST, and I choose the best neighborhood. That's an option, but that's very time consuming. So possibly it's not the solution to retain. I don't know. We'll talk about that later on. Another option is why fixing the value of H. We can understand to fix it to 12 because it's a good trade-off, but possibly it could be also nice to have a dynamic value of H depending on the point of the search at which we are. Maybe at the beginning, larger or smaller, maybe more smaller values of H, and at the end of the process, maybe larger values of H, possibly. We don't know. And another remark is that it's really time consuming. This is a point where you have to take care about when you deal with Mathuristics. And trying to save time is a big deal. It's something really important. And I think last thing to say is that, in my opinion, considering windows of position makes sense for permutation problems. So as long as your scheduling problem is a permutation problem, so let's go ahead, go and proceed with VPLS. It's a good option. And okay, VPLS can also be extended to other problems when you have an assignment. So if you have parallel machines, for instance, you have assignment and scheduling at the same time and sequencing at the same time, you can do VPLS too. You can say I have a Windows and I just consider a portion of my schedule that I want to re-optimize. But due to the assignment, I don't think it's necessarily a good idea to do like that. We may more use another approach to fix variables, and this other approach relies on the Hamming distance that we have seen before. Possibly it's better in this case to define the neighborhood based on the distance and just say, here is my schedule, please don't change no more than n jobs or assignments with respect to my current schedule, and try to re-optimize around that. That's possibly more flexible. And here, clearly, the neighborhood is defined as all the solution X that are no more that have no more than k change in the vectorial variables. So what you have to remind is that this neighborhood is larger than the neighborhood when using the windows of positions, much larger. So intensification is expected to be more time consuming. So, okay, it's more flexible, possibly more powerful, but you may do less iteration in the same amount of time because of the time you spend in intensification. Okay, so that was things around intensification and scheduling problems. Now I would like more to bring your attention on diversification and how this can be done and how this can be efficient in a Matheuristic framework. Diversification is very simple. You are in a neighborhood, you are stuck in this neighborhood, so the only thing that you want to do is to get out of this neighborhood and find a solution which is somewhere else in the search space. So if you have a distance-based neighborhood, it's quite easy because you just have to say, okay, I have my Hamming distance, and now I will just impose that with respect to xt, my current solution, I change at least k variables. So you change at least k variables and you provide me another solution. We are out of the neighborhood. A perfect example of Matheuristic using diversification is local branching that maybe you already heard about. Local branching uses both intensification and diversification. Consider the Hamming distance we've discussed so far. Local branching has been first introduced by Fischetti and Lodi as an exact branching algorithm for which it's easy to derive a Matheuristic framework. I will not deal about local branching as an exact method, but just as a Matheuristic. And classically, what is assumed in such an approach is that each time you'll call a MIP, you'll have a time limit so that the MIP will not go until the end or within the limit of time, let's say. And we'll have a parameter k, which is the given radius, so the number of variables that are allowed to be changed with respect to the current solution. And we'll also have another parameter, which is L, which is the radius used for diversification. So K and L may be different for sure. So local branching works as follows. You have an initial solution, S0. And first, you generate one branch on which you say, okay, I'm looking into my neighborhood. So I'm looking for a solution, S1, which has at most K changes in the variables which are associated. K changes with respect to S0 and X0. So I add this constraint to my solver and I solve the IP. And then I get a solution X1, and so S1. And when I've done that, I'm happy. I have a new solution which improves S0. And then I generate a second branch. And I say, now I want to explore outside of the neighborhood of X0. And so I add the constraint to my IP that now the Hamming distance is greater, Hamming distance from X0 is greater, strictly greater than K. And at the same time, I add the constraint that the Hamming distance with respect to X1 is at most equal to K. So this corresponds to exploring the yellow area on my figure here. And you solve the IP associated to this new problem. And you get a solution X2. And clearly, you do that until hopefully the end. But it may happen that at a point when you solve the IP, you reach your limit of time and you don't get a solution. The solver says, okay, I found now a solution in this yellow neighborhood. So what you do is that you say to the solver, okay, guy, K maybe was too large. So solve again the problem, but with the value K/2. So you decrease the size of the neighborhood and you restart the solution in this smaller yellow area. If still you don't find any solution, so you arrive to the conclusion that, okay, maybe you are stuck into a local optimum. So you are applying diversification. And diversification is just adding the Hamming distance when you say, okay, now I want a solution that has at least L changes in the variables associated to X with respect to X2. We solve the MIP and we get another solution X3. If no solution X3 is found, then you stop. And then you redo the search from x3. And that's exactly this process that you repeat until the end, until you reach your time limit. Well, Viscati and Lodi suggest to use soft diversification, which personally I found on my experiments pretty useless, but why not? And next, if it doesn't work, to use strong diversification, which is, in my opinion, more efficient. Even if they suggest to use L equal 1, in practice, it's maybe more efficient to use a greater value than 1. Okay, and there's also some stopping rule that you can add. So there are a lot of variations around that, but that's the main principle of local branching. If you look now to scheduling problems, well, I found almost nothing. Just a paper published by Yang and Roll in 2021 on an hybrid flowchart problem, but they didn't use any diversification. So to give more details, to present an application of local branching, I finally decided to use not a scheduling problem, not to consider a scheduling problem, but more a problem that was used with, on which I worked in the past. So it's not scheduling, but it's not far. You see, it deals with assignment. So this problem is the following. It's called the graph edit distance problem. I give you two graphs, G and G prime. And the question that I ask you is, how much G resembles to G prime, okay? And to know how much G resembles to G prime, what we will do is that we will match vertices of each graph together. We will match some edges, and we may also remove some vertices and remove some edges. So we will kind of transform graph G into graph G prime, and we will count the number of operations that we did to do such a transformation. And each operation has a cost. So you want to find the transformation with the least cost. In the JED problem, we have a cost for deleting or creating a vertex, which is assumed to be a constant tau. We have a cost for deleting or creating an edge, which is the same constant tau. And we have a cost CGK for matching vertex G from graph J from graph G, and with the vertex K from graph G prime. And so we want to find a matching which minimizes the total cost. That's quite simple. That's kind of a particular assignment problem. Well, to design a local branching heuristic, what we did is that we used an existing IP formulation, which is in fact quite effective. It has been proposed by Justice and Hiro in 2006. I don't go into detail of this very particular and tricky formulation, but just to tell you, it's based on Boolean variables xij equal 1 if vertex I is matched with vertex G, and also we use Boolean variables Sig and Tig to represent edge deletion or adding, okay? But what is clear when you look into this formulation is that the key variables are the Xij variables. When you have matched the vertices, then you have done your job, because then you know what are the edges and the vertices that you need to remove from G or to create from G. So we will focus on the Xijs. To initialize the local branching, what we did is that we solve the IP of Justice and Hiro with a short time limit. We say, okay, Guy, you have like 10 seconds, give me the solution that you have, that you computed so far. Neighborhood definition, that's clear. So it's just the Hamming distance on the Xij variables. Intensification, we have the IP. And what we did is that if after our time limit T node, we have no improving solutions, then we decrease the radius to K over 2 and we solve again the problem. So hopefully trying to find an improving solution in this reduced neighborhood. And if this fails, then we apply strong diversification. Because, well, we did experiments of diversification was totally useless in this problem. Strong diversification, well, we find out that it was more efficient not to apply diversification or the Hamming distance on the whole set of variables xij. But we more focused on the subset that we called the subset of important variables, the SIT, set SIT. How to determine these important variables? First, what we do is that independently of the current solution xt, we compute a matrix MIG, where MIG is a lower bound on the cost of matching vertex I with vertex G. So MIG is the sum of the matching cost of the vertices plus theta ig, and theta ig is a lower bound on the costs induced by matching the edges from I with the edges from G. So you have here an assignment problem, and you just solve this assignment problem to minimize the cost of assigning these edges. And among all these values, for a given vertex I from graph G, we compute the standard deviation sigma I over all the values MIG for fixed I. So the idea of the standard deviation is to say, I have my vertex I in my graph G, and I would like to identify which are the vertices which, if I change their assignment, then there's a high variability in the objective function, in the matching cost. So these will be the important variables for diversification. So I do a binary classification of these variables based on the standard deviation, and I identify the class of the variables having the largest standard deviation sigma I. This gives my set SIT. And what I do is that I said, okay, now for diversification, you change at least L of these important variables with respect to my current solution xt. And this is diversification. So you really put a kick in the solution and move somewhere else in the search space. And we stop after maximum time limit T solve is reached, or you have done a maximum number of diversifications. So we did some experiments on two databases of graphs which represent chemical molecules. So chemical molecules, you can represent each of these by graph, and somehow you want to know which are the molecules which are really similar to each other. And this is done by solving the graphite distance problem. On the first database, which is quite a small one, you have graphs with up to 28 vertices, okay? And we have this tuning for the Matheuristic, okay? And for the second database, Muta, we have larger graphs, up to 70 vertices in size, and with the different tuning of the Matheuristic. And we ran the experiments. And on the PAH database, the average CPU time of the Matheuristic was 3 seconds, and the gap to optimality was less than 0.35%. So here, the Matheuristic was really, really close to the optimal solution. And 76% of the time, the instances were solved to optimality by local branching. On the hardest instances, what we have is that the CPU time for sure is much higher. We were more about 750 seconds on the average on the largest instances. And the gap to the best known solution was, let's say, below 0.8%, which is still very, 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 very low. And in 2021, this Matheuristic was outperforming all non-heuristics for this problem. So it was really good. Well, so if I do a first pit stop, I would say that these heuristics are really efficient in practice. Seriously, you should consider them when solving a scheduling problem. Either you have assignment or just sequencing, or both. But there are some points of attention. First, the choice of the IP is crucial. Fast convergence toward an optimal solution is much better. It's preferable. Also, each time you use the IP in your Matheuristic, don't leave the solver, even if it's called on a subproblem, don't let it running until the end. Often it's better to say, oh, I just let you like 20 seconds at most of computation, and I keep the solution that you return me. and I continue my process with that. It's often more efficient. And the choice of the variable st is also crucial. I mean, you should put in the process the variables that really generate the combinatorics, and maybe not all of them at the same time. So it's another point of attention. Really take care about that. I would say that the drawback is that you have some parameters to experimentally tune, like the choice of R, H, K, L, whatever you want. You have some parameters, and you need to find a good trade-off between minimizing the number of iteration and the total CPU time. So tuning these parameters is not always easy, and may require from you some preliminary computational experiments. Spend some time on that. My conclusion is that also diversification seems in practice really to be useful. So it should also be considered always. Well, the point is that it's time consuming. How could we improve that? Because what we would like is to have efficient heuristics that scale to large instances. Well, one way to improve that is trying to limit the number of useless neighborhoods that you explore. If you think about VPLS, the choice of the random choice of R was not for sure necessarily a good idea, but maybe we can try to improve around that. Also, try to limit the size of the IP to solve. And in this sense, VPLS is more suitable than local branching, because with the Hamming distance, your neighborhood is really, really large. So if you can limit the size of the neighborhood, you'll save time also. Another option is possibly to adjust the size of the neighborhood dynamically, maybe starting with small size neighborhoods and then considering larger neighborhoods in the end. Possibly it's a way to save time without losing efficiency. Another place where we could maybe find answers to the question of speeding up the Matheuristics is considering machine learning. Maybe we could use machine learning to answer some of the questions or some of the points that I put earlier. Let's see what I have in mind. The goal, one possible goal would be to find, by means of machine learning, would be to find the most suitable neighborhood to explore from an incumbent solution, ST. So if we go back to the two-machine closure problem and VPLS, well, we have this notion of neighborhood, my window of positions. So R defined by R and H. Can we use machine learning to predict the best R and H for a given sequence ST? This would be kind of magic. You know, I give you ST and you give me, oh, consider this value of R and this value of H. That's the best you can do. Well, if we can do that, I think everybody will be happy. So that's the ideal goal, having such a predictor capable of predicting R and H when the predictor knows ST. Let's say that first will be more reasonable. We will just consider the case, okay, if I give you R, H, and a current solution S, can I just say if reoptimizing this window of position leads to a better solution ST plus 1? And if I just can answer on this question, then it's not that bad. So let's focus on the second question. To do that, we'll use structured machine learning to solve this classification problem. Okay, if the answer to my problem is now just yes or no, does it improve or not? And so we'll use an approach based on features. So what we'll need is for any solution S and parameter values of the parameters R and H, we have a vector phi of X of features, so of values which describe the solution S and the associated values of R and H. And as you see, we have set 90 features. I'll talk a little about them later on. And from this vector of features, phi x, we want to build a predictor P of phi x theta star, which returns a value between 0 and 1. And theta star is the vector of weight in my model. It's the vector of weights that I have to learn. And clearly what I'll consider is that if P is greater or equal to 0.5, I'll consider that the answer of the predictor is yes. And if it's lower than 0.5, I'll consider that the answer is no. The predictor P that we consider is a neural network, and with the theta being the weights associated to the neural network. That's for a general description of the machine learning part. And for the features, so that's a key point. We have two kinds of features, what we call descriptive features, which are very basic, like starting times of the window, C1 and C2, number of job, the ratio between PG1 and PG2, this kind of very straightforward things. And we also put some more informative features like computation of lower bounds or upper bounds on the window if you just re-optimize the window. So well, we were trying to be creative when designing these features. And then we use these features as the input of a neural network, which is a pretty small model with just 14,000 parameters, no, 140,000 parameters to learn. Okay, it was a CNN model. Next, we have our structure, we have our features. Now we need to generate databases for training, validation, and tests. So what we did is that we randomly generated 1,000 instances of the scheduling problem for given values of n between 15 equal to 50 or 100. And each time we ran the Matheuristic, and for all the possible windows R and R plus H, we test them, and each time we report, okay, this window on this solution yielded to an improvement or not. Meaning that we had in our database 180,000, more than 182,000 schedules and time windows, and that about 35% of them were positive time windows, so improving time windows. And this was our 3 databases that we used to train and test the neural network. So after doing all the training, what we have is this confusion matrix. It reads like that. If I have a window that doesn't re-optimize for a given solution, 72% of the time, my predictor said, don't re-optimize. That's not bad, okay? That's not fantastic, but it's not terrible. And also, if a window re-optimizes, leads to a better solution, then the predictor 64% of the times said, okay, go, you can re-optimize. This is a bit less, it's not that efficient. So globally, my opinion is that the model that we had at the end was not bad, but it was not fantastic, okay? But still, we wanted to see what happened if I use this predictor in the Matheuristic. So we did, we compare 4 versions of the Matheuristic. There is the original one, and there's the 2 last one. The MLVLPS is exactly the same that the original one. So you generate at random a value of R, you call the predictor for H equal 12, and you follow the predictor. If the predictor says re-optimize, you re-optimize. If the predictor says you don't re-optimize, you generate another R value, okay? And there's the last version in which you generate all, for a given solution, all the possible windows of positions. You call the predictor each time, which is pretty fast, and you select the 70% best interval, 70% of the best intervals. And you re-optimize all of these intervals, and you keep the best solution among that. So it's kind of an exhaustive approach that compensate the fact that the predictor is not always very efficient, notably with positive predictions. And the results that we have in 60 seconds of processing times are the following. So clearly the original VPLS is the most efficient approach, but it takes on the average 60 seconds. Okay, it needs to go until the end. The version using the predictor, so ML VPLS, is less efficient. Still, it returns good solutions. It's the average deviation is at 0.0187% of the best solution. So it's not a bad heuristic, but it's not the best. And the last version of machine learning VPLS Plus is very comparable in terms of efficiency to VPLS, but I think the advantage that is really fast. On the average, it took only 7.38 seconds to solve the problem. So we have here something which is efficient and fast. And these results generalize quite well for higher values of n. So that's, I would say, not a good news, not a bad news, but a promising way of research. It's interesting to make the VPLS converging faster. So I'm near a conclusion. I have a second pit stop. In the design of faster Matheuristic, I think that really machine learning seems to be an interesting approach to drive the search. It was not enough efficient in the above example, but well, we're still working on that. And one thing that we are looking at is that the notion of a good neighborhood. In the Matheuristic, you say the first improving neighborhood, I keep it, and I continue with the best solution that I got from this neighborhood. But possibly it's a bad idea to do like that. Possibly you should have an idea of what happens after a second time and a third reoptimization. So 2 or 3 iterations further to really know if keeping a solution was a good in your neighborhood was a good decision. And so this is the way we are looking at the thing, trying to get information on the next iteration and learning based on what we get 2 or 3 iterations further. And there are also many other possible use of machine learning, variable selection, determining values of parameters in local branching. Well, I'm sure you'll be creative if you're interested in continuing in this direction. Well, time to conclude. So we've seen 2 examples of Matheuristic conceived as local searches, okay? And if you look at the literature, you can see that there are some papers, and I put there papers dealing with Mathuristics and scheduling in a large sense, okay? So sometimes it's routing and scheduling. But you also have papers on constructive heuristics and also on evolutionary meta-heuristics, and also some papers that were unclassified for me. So if we have to sketch the pro and the cons of Matheuristic, I would say they can be very efficient. So this is something that you should keep in mind. They are really easy, at least, to set up. I mean, maybe not tuning exactly the best parameters, but it's really easy to say, oh, I set up a Matheuristic with basic parameters, and I see what I have in the end, how good it is. And also, you can use non-commercial IP solvers. It's okay. I mean, it's not like if you would have to solve to optimality the problem. So you can use non-commercial solvers. The cons, well, it can be time-consuming. We've talked about that, but we'll also sketch some possible ways of improvements. So the consequence of the time requirement is that they may have difficulty to scale up to large size instances. That's it. And we also have a bunch of parameters to tune if you really want to have a super effective Matheuristic. So the tip of the day for me would be the following. If you have to solve a problem heuristically, and if you have a MIP, which is not bad, well, spend half a day, spend a day and just set up a Matheuristic. And this will be a very good basis for comparison for other heuristics. And outperforming these Matheuristics, I promise you, it should be really difficult. So that's a good starting point, I think, for heuristic solution of scheduling problems. And I think it's all for today. Thank you for your attention. If you have any question, I'm here.
Okay, thank you very much. I will just allow participants to unmute and ask questions. So if anybody wants to ask, please go ahead.
May I ask a question?
Go ahead, yeah.
Sure. So I'm Nasser. I have just a question to just understand the math heuristics. So sometimes, for example, we develop a branch and price algorithm to solve, for example, a scheduling problem like flow shop. So sometimes we use meta-heuristic to solve sub-problems until that when this, the meta-heuristics cannot provide, good solutions for meta-heuristic, then we shift to just use, mathematical models to solve them optimally. So can we use these, consider this method as a math heuristics, or just, I know that it's a vice versa. So we use, meta-heuristic, then we have mathematical modeling, but can we classify this as a part of maths heuristic based on your experience?
Well, you mean using an IP solver inside of branch and price algorithms?
Yes. So sometimes when we are not, because it's time consuming. So rather than using, it's the base, the construction is a branch and price, but sometimes in order to provide solutions faster for solving sub problems, we use meta-heuristics at first to solve sub problems. Yeah. Until the time that we cannot get a good solution, then we shift to use, mathematical model to solve them. Yes. Yeah. So does it count as a math heuristics algorithm?
Well, math heuristic is just solving in a heuristic way a problem. So I would say that in your branch and price approach, the one you mentioned, instead of using first your meta heuristic, well, just solve a math heuristic. And if it fails to find an improving solution, then just pay for the IP. Right. But possibly, if your IP formulation is not bad, you may directly with the math heuristic find, let's say, the optimal solution that you would get by solving the IP. But you will not have the proof of optimality, but at least you will have a very good solution because it's quite close to solving the IP.
Correct. Yes. Yeah. Thank you.
Okay. Next question, please.
Yes, I have a question. Yeah, thank you for a very nice talk. Do you have any experience using constraint programming instead of mixed integer programming?
Oh, that's a really good question. In fact, that's obvious. Everything that has been presented here can be translated in constraint programming. You replace the IP solver by a CP solver. So you can keep the same ideas, the same mechanism based on local branch, based on the distance, based on variable fixing, everything. And for sure, you can have what we could call CP heuristic to stick to the same kind of name. So you can do that. I have to be honest, I didn't look at the literature trying to find papers on constraint programming and heuristics in the sense they are doing something similar to Matheuristics, okay? So I can't say if there are a lot of papers or not. My guess is that no, there's not so many papers. There are papers on CP and heuristics, but not many papers, I think, doing heuristics with the same mechanism that the one I presented today, okay? Personally, we started with a colleague here to look, but it's very recent, to look at what we can have if we do such a CP heuristic, like using local branching. But it's still top secret, so no information given today.
Yeah, thank you for sharing your secret.
Oh, no, I said nothing, okay?
Okay, thank you. There was a very similar question in the chat, so you responded it just now. Huh?
Okay.
So the next question, please.
Okay, go ahead. Let me ask you a question. First, do you have any knowledge of math heuristics being used in industrial scheduling systems? So industrial scheduling systems that have time limits, that they have to produce a schedule, let's say in 10 minutes on their computer. And how does the math heuristic then compete with a purely genetic algorithm on in industrial scaling systems? How much better do you do? I suspect that you will do better than a genetic algorithm, for example. But how much better do you think you will do?
Well, there are more than one question in your question. So let's start from the beginning. Well, we applied Matheuristics on industrial problems, okay? And it gives really good results. The problem, there are two problems. It's time consuming, which somehow can be managed, okay? You set a time limit of something like a minute, and the decision maker can wait a minute. Possibly if you tell him to wait, he may wait a minute. The second problem is that you use the commercial solver. So that starts to be maybe costly for the company. So in an industrial context, there are these 2 points you must address, you must take care of. Now, if you try to compare that to, I would say, first, fast meta-heuristic, not necessarily genetic algorithms, it's possible that it's in favor of the meta-heuristic in the sense that if you have really large instances, it's possible that the Matheuristic is really time consuming. If you hope to set up a Matheuristic that works in, like, let's say, less than 10 seconds and be very efficient, it's really rare that you can achieve this goal. Possibly the Matheuristic will require much more time than 10 seconds to run. So on large instances, it's more in favor of meta-heuristic instead, unless you find a way to speed up your Matheuristic. So that would be a first comment. And my last comment would be that with comparison to genetic algorithm, there is no way. Genetic algorithms are also really time consuming. So if you take the time budget that you're ready to spend on a genetic algorithm and you give this time budget to a Matheuristic, I can bet you a restaurant that the Matheuristic will win.
Okay, thank you. Very, very enlightening.
Okay, thanks.
Okay, next question, please.
I have one question. I would like to ask regarding the local branching, because we sort of, when we run local branching for some time, we explore a lot of space of the solution. So if there was like a huge time limit, is there like a way how to do this sort of in an organized way, so we don't have to, when we want to find the optimal solution to the whole problem, we don't have to sort of restart everything with the model unconstrained by this, but is there like some smart way how to note which neighborhood was already explored and sort of systematically expand this until all of the search space is like explored?
Well, tell me, I'll give you an answer. You'll tell me if this is the right answer to your question, okay? I think that in local branching, you know, when you go on the branch on the right, you say, I want to explore now the search space, which is outside the neighborhood in which I was. So you say, the Hamming distance is greater than K. Yeah. And you re-optimize, trying to be at least at most at the distance from K from the best known solution. When you do that, somehow you just withdraw some part of the search space that you forbid, because you keep all the constraints, all the previous constraints, you keep them, especially the constraints saying, I want to be at least at K changes from the previous solution on the branches on the right. Yeah. Okay, maybe I can put, okay. And then you'll not go back into the same space, part of the search space. After that, if you keep all the constraints in your model, the problem may be that you'll have a very big model. So it will be slower and slower and slower as your search goes on.
I see.
So this is a trade-off you have to accept. Either you may go back to some part you already explored and you don't keep all the constraints, or you keep all the constraints or a subset of the constraints to forbid going back to known places. This has to be tuned experimentally. I don't have any more precise answer than that.
I see. Thank you very much. And could I ask you to jump to slide 20? There was like this graph of this, and I just want to ask one particular question, if I understood correctly, if that's possible.
20, you said, okay?
Yeah, it was slide 20 out of 46. Yeah, and here I maybe misunderstood the explanation, but the circle around the solution S1 overlaps with the circle of the solution S0, but we enforce the condition that it must be further from the S0. So I'm not sure what does the circle mean. Shouldn't like the overlap of these circles actually be removed when we looked in under the branching node 2, like in 3 or 4?
Okay.
This.
Okay, so let me explain. The circle, the area in the circle is the neighborhood around the solution. So you start from S0 and you have the first gray circle, which is the neighborhood of S0. And then when you go to node 2, you say delta of x0 must be greater than k. So you say, I don't consider the solutions which are in the neighborhood of S0, okay?
Yeah. Yeah.
And then you go to node 3, and in node 2 you solve nothing. Okay, you solve only on the left nodes. So you go to node 3, which is a left node, and then to go to node 3, you say that the Hamming distance between x and x1 is at least k. So you take S1 and you draw the same circle around S1. So you'll have a part which is common with the neighborhood of S0. But this part has been removed by the second constraint. That
I see. Yeah.
And so it only remains the part that is below S1, which was, in fact, if I go back maybe more to this, we'll say, here, sorry.
Yeah.
You see the yellow part here?
Yeah.
The yellow part is the search space that remains after having set the constraint that you are further than k from x0 and you are closer than k from x1.
So the overlap of the circles is actually not checked again.
It's not considered. It's excluded from
now I understand.
The constraint from x0.
Okay. Thank you very much. And very interesting talk. Thank you.
Thank you.
Okay.
Hello. I have another question. This question concerns the idea of good neighbors that you mentioned. And my question is related to the first example that you made with neighbors with different R and H. These are different neighbors, but they share the same framework, the same structure, let's say. So there could be a lot of overlapping. Do you think it will be more promising to use what I can call orthogonal neighbors, meaning that these neighbors move along a different direction in the solution space and do not have a large overlap among each others?
Yeah. We could think about something like that too. Saying, for instance, it's maybe useless to consider the neighborhood where you have R and the other one with R+1 because they are almost the same. So you could say this, I don't want to consider these two, I may just consider one of the two, but not the two at the same time for a given solution ST. That's possible, yeah? And so starting from this, this statement, we can arrive to an approach, as you say, consider like distinct time windows of positions, and each time re-optimize and maybe keep the best solution among all the optimizations. That's an option. You just have to remember that if you do that, you'll solve several re-optimization problems at each time. So that's a cost that you must be ready to pay. Possibly it's a good choice, but that's a cost that you must be ready to pay. And the other point that I see, but which is also valid for the current Matheuristic there, is that what makes a good neighborhood? Are we sure that the strategy of the first improving neighborhood is the best strategy? So starting from that, if you generate k neighborhoods on the same solution and you explore these k neighborhoods, what is the rule for selecting the next solution? We're not sure that selecting the neighborhood, giving the best solution is the best strategy. And I can tell you from experiments that are still top secret that it's not the best strategy. So this really asks the question about how to select the neighborhoods, whatever is the way you select the neighborhood. I mean,
Okay,
whatever
thanks.
is the way you say the R. It's a more global question than that. I mean, I don't know if I was clear, but it's for me.
Yeah. Thanks.
Okay, thank you. Any other question? If not, let me ask also. So, to which extent do I need to incorporate some expert knowledge of the problem to decide which variable is good, what is K, what is R? Is this approach completely generic? Like it can be even incorporated inside of Cplex and then it would work for whatever type of problem? I will just tweak some numbers and then it will try to make it, or to which extent do I need to incorporate my prior knowledge of the problem? And is this knowledge needed for this neighborhood selection or for diversification phase? Or if you can a little bit brainstorm on that. Huh?
Yeah, that's a good question. If I want to provide a short answer, I would just reply to you, oh, that's exactly the same debate that for any meta-heuristic.
Yeah.
Okay. So Mathuristics are general kind of heuristics. So it's a general framework. But at the same time, it's for sure, if you integrate problem knowledge in the method, that's clear, you'll improve your algorithm. So yeah, it could be possible just to add Matheuristics in Cplex, for instance, or in Guohua or in Express. It's pretty easy. It's generic. But if you really want to have something that is efficient or to improve the efficiency of the Matheuristic on your problem, you definitely need to integrate knowledge from the problem. And this is something, for instance, that what we did for the JET problem when we dealt with the diversification and the selection of the variables. And you're right. Basically, you can try to identify from the problem which are the variables that matter. So the ones that on this solution, I need to play on these variables to improve my solution. So if you can put knowledge from the problem there, I think you get something very interesting. And for scheduling problems, it's easy. It's like, oh, I can look at a part of my solution, and this is part of my schedule that I want to re-optimize because that's a critical part, because I have some bottleneck machine at this point or whatever. You can have any reasoning that you want to try to identify variables on which you do intensification or even diversification. For the choice of the neighborhood, it's a bit more complicated. And I think I don't have any precise answer to give you, but I think it's not necessarily related to scheduling problems, but more on the behavior of the Matheuristic on your scheduling problem. What is the best strategy? I have no idea on how to integrate knowledge information from the problem.
Maybe that's philosophical question as well. So it's above of our capabilities. Okay. So any last question? Paolo Detti unmuted himself. Don't you want to ask anything, Paolo?
No, thank you.
Okay, so thank you very much. It was very interesting debate and very nice talk. And now let me just remind what will be the next talk. It will be given by Young Kim from KAIST, and it will be in 2 weeks on March the 1st. And she will speak about scheduling and machine learning. Okay, so we will be again attracted to this AI topic. Thank you very much for listening. Thank you, Vincent, for very nice and inspirative talk, and hope to meet with you in 2 weeks. Okay, bye-bye.
Thank you very much. Bye.
Bye-bye.